Yeah, it's interesting. Earlier in the lab, it was raining so hard that I had to speak really, really loud just to improve the signal-to-noise ratio. That's the engineering term to refer to that sort of thing. All right, so going straight to the content of today's class. All right, so are there questions that I can answer? No? Okay. All right, so we are going to go into clocked circuits. But before we do that, let me remind you what we have talked about already. And we can do this in a reverse chronological order, starting with the very last thing that we talked about in the previous class. And I think we looked at this diagram last time, right? This thing here? Correct me if I'm wrong. Yes? Okay. So with this picture, each one here, each smaller box, is a 1-bit edge-sensitive, resettable, gated D flip-flop, which means you can use it to remember 1 bit. Okay? But when you look at this entire circuit, all of these 1-bit D flip-flops, they're all interconnected in a certain way. They share the same clock, they share the same enable, and they also share the same reset. So as far as those 3 control pins are concerned, they function exactly the same way. The only thing that is not shared are the data pins and also the Q pins. The data pins, which serve as input, we are coming in from an 8-bit input pin through a splitter. So bit 0 only goes to one single D flip-flop. Bit 1 goes to another D flip-flop. Bit 2 goes to another D flip-flop, and so on. And then the output of the D flip-flops, they're also going into a merger to merge back into an 8-bit output. So this is what we kind of use as a 8-bit register in Logic. But this is kind of like the inside view of an 8-bit register that we can use in Logic. Is that okay? Yep.
So the reason they're all enabled is because the entire register has to be activated at the same time?
Right, because the entire thing is functioning as one single unit. So we are no longer differentiating between the individual bits. When we want to update, we want to update all 8 bits at the same time. In other words, if each one is one single instrument, we are looking at one section of instruments. So they serve as one single unit when we are operating the processor. Yep.
Couldn't we have just taken one edge-sensitive D flip-flop and changed the data input to be able to take 8 inputs?
I don't think so, because all of the other gates also have to increase to the number of bits that are needed.
Oh, because of the...
Right, because the data bit goes into a particular gate.
Yeah.
So when that gate changes to 8-bit wide, it impacts all of the other gates that it connects to, and also what gate connects to that 8-bit gate. So when you change the gate bit width, you have to change everything. Okay. All right. So schematically speaking, this is what the conclusion of our last discussion, and then we go back to a single bit like this, and then we go back to a non-resettable one like this, but it is edge sensitive and is gated, and then we go back to the previous one, which is just clock or edge sensitive. This one does not have a diagram, but I did display the diagram in class using Logic. And then we go back to a level sensitive design, which is just called a D flip-flop. And then we went all the way back to a SR latch, and which is one of the simplest memory devices that you can make out of logic gates. So that's kind of the backstory of what we have gone through at this point. But getting back to the last picture, okay, this clock is important, okay? Just something being clocked or edge sensitive is really important, because now we have the most basic mechanism to make a clocked circuit. So right up to this point, every circuit that we make, no matter how complex, are not they're not clocked. So your adder is not clocked. What does it mean? It means the operation is what we call asynchronous, or you change the input after a certain latency or delay, the output will update. Okay, so now we want to look at a very simple circuit that is clocked, but there's no way to implement it without being clocked. And the circuit that we want to implement is called a counter. And let me go start the logic sim from here. Oh, it's java.jar logic sim, and I cannot remember where I put the file. I think it's in temp folder. Yep, there we go. Okay, so we all recognize this circuit, right? This is a SR latch. So what we'll do today is I'm going to re-implement the entire thing because I don't want to just show you the picture. So we'll call this counter 2, okay? Because I have a counter already for the Monday, Wednesday class. So they have kind of caught up already with us, which is kind of cool. Okay, so with the counter, we need only 2 components. Well, 3 components to be exact, but 2 main components. The first component is an adder. So we go to arithmetic, we pick out an adder, and we just kind of slap it somewhere here. And then the second device we need is from memory because it's a register. So we go to memory devices and select a register, and we just kind of slap it here. Now this is the time when we go like, okay, but we have never seen or used these components before. How do I know how to make use of these particular devices? LogicSim turns out to have a really, really good help manual. So when you go to library reference, it is structured the same way as the component structure. So you can look up in memory library, you can look up a register, and that explains to you, what each port means in a register. But we are going to play with a register today, so you can ask those questions today as well as we utilize a register. The other thing that we are utilizing today is an adder. So you go to the arithmetic library and then you click on adder, and this will also explain all the different pins, what they do, the significance, what if you don't connect anything to it, what's going to happen, that sort of thing. So I strongly recommend that you guys start to look into the documentation that's built into LogicSim. Okay, so here's the next question. In the next exam, in exam 2, we know for sure that LogicSim is going to be a component of that, okay? So there will be questions involving registers, adders, multiplexers, demultiplexers, and so on. And the so-called notes is actually in here. So now the question is, how do you get this onto a piece of paper? What do you think? You can copy and paste it, which is painful. That's a better way. That's an easy way to do it. So I'm going to show you that way first because some of you may want to print something and put it into your binder. For those of you who are kind of more paper and tactile. So let me go to my home folder and I'm going to copy LogicSim. Okay, you cannot see that. There we go. Okay. So I'm going to open a new tab here. So what I'm doing is I'm copying the LogicSim jar file into a zip file. Okay, so we just call this logicsim.zip. Okay, so in Windows, all you're doing is you're clicking on the name of a file, but you have to remember to change the extension as well. Okay, because with Windows, the extension dictates what you can do with it. So without changing the extension from jar to zip, Windows will refuse to look at the file as a zip file. In Linux, it's not important. Okay, I can do unzip on any file as long as the file format itself is really a zip file. Okay, so once you do this, I will make a subfolder first. Okay, you don't have to do the same thing, but I'm going to create a subfolder, and then inside the subfolder, I'm going to unzip logicsim.zip file, and it creates a whole bunch of subfolders. And this is why I created a subfolder, because everything is inside a multiple subfolders. So if you don't create a subfolder first to contain these subfolders, it's going to be expanded on your documents folder or some place that you don't want to mess with. Is that okay? Okay. So out of these folders, which one stands out because we are looking for documentation? Doc, exactly. I'm not just a doctor, I am the doctor. Well, if you watch Doctor Who, you know what I'm talking about. I think the Christmas special is really cool for 2017. So anyway, right here we can go to EN, and you can see that there are multiple languages as well. So if you want to use the other languages, feel free. I mean, it's your choice. It's just that when you present your answer in your test, I can only understand English. If someone presents the solution as in Spanish, I cannot read that. All right, so, and at this point you go to HTML, and we have the usual stuff that we are familiar with, right? So now you can just point your browser to index.html and find out what happens, okay? So we'll go to my browser, okay, which is already open, and then we can specify to open it at that location. Let's see, I think I have to re-enable the menu bar. Okay, how do I re-enable the menu bar? Okay, there might be another way to do it. File, : / Okay, where's that gonna get me? Okay, cool. That will get me to where I need to go. Just have to go to home. It's under Logisim. Did I miss something? Huh? Oh, okay. So it's time-based. Okay, and then under here we go to doc, and then en, and then HTML, and then index.html. All right. So now you just go to library reference and go to whatever you want to look up. So if we want to look up adder, here's the adder page. It is a page on its own. So if you want to print it, you just do a Control P and send it to your printer. So this really helps because now whatever component we are going to use in this class, you know exactly where to find the documentation for that component. Is that okay? Now, if you read this documentation and you don't understand a certain part of it, bring it to the class. Okay, we can talk about it in class, or you can present it in the lab and go like, okay, I'm not really quite sure what they mean by da 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 da, and I can explain that. But the main source of information as far as the components are concerned is from Logisim itself. Yep.
Would those pages go on Canvas?
Do you have Logisim?
Yeah.
Then you have these files already. You just have to do what I did to get to the files. So I would just say that go get your own. Because if you have your own, you can start to edit it as well. So you can export this into a doc file, and then you can start to annotate and add your own notes. So that's the valuable part of having your own version of these files. All right. So are there any questions about how to get to the documentation that is built into Logisim? No questions? Easy enough? Okay. Well, I really do have to ask that question because years ago I had one student who got an A in cisp 430. That's how she met the prerequisite for this class. This class only needs cisp 360. If that particular student aced cisp 430, at the end of the entire semester, the last homework assignment involved me giving the students a particular zip file. So they expand the zip file, they modify one or two of the files, and then they turn in the final project. That student could not unzip a file at the end of the entire semester. Now, you have to understand that person did not take a cisp 430 from this campus. But that's why I have to ask. So are we all comfortable with unzipping a file? Okay. Because I don't want someone to ask me, so where's the zipper? Okay. So this is the adder. Sometime, probably sometime next week, we'll start to get to plexers. Particularly, we'll get into multiplexers, demultiplexers, and decoders. So all of these will be interesting things to print out, okay, or read if you want to read ahead of time. But today, we are not going to talk about these. We'll be focusing on the adder and the register first. So let's go to the register and find out exactly what a register has and how it resembles things that we have already talked about. So we go to register, and let me just kind of magnify this a little bit. Okay, so it says right here that a register stores a single multi-bit value. In other words, the entire value is treated as one single thing, and it is displayed in hexadecimal. So whatever digit you see in the register is the content or the value that is stored by the register. It is emitted on its Q output, which means this pin here, this port, is the output of a register. It serves the same purpose as Q in our D flip-flops. Okay, it's the output. When the clock input indicated by a triangle on the south edge, which is this one here, when indicates so, which means it's either a rising edge or a falling edge, it is programmable. Okay, when you place a register in Logisim, there's a property that allows you to specify, do we want rising edge sensitivity or do we want falling edge sensitivity? So you can choose, but rising edge is the default. The value stored in the register changes to the value of the D input, which is this one here, which is also consistent with our terminology in the D flip-flop explanation at that instant. Exactly when the clock input indicates for this to happen is configured via the trigger attribute. So it's the edge sensitivity, rising edge or falling edge. The reset pin resets the register's value to 0 asynchronously, which means it is not waiting for a clock to rise or fall. That is, as long as reset is 1, the value is pinned to 0. It is locked to 0, regardless of the clock input. So that's basically the explanation. And let's go back to Logisim. I just missed it. There we go. And we're going to do some interesting connections here. We want to do an add one circuit. Now this the adder circuitry has a carry in and also another input. So this is kind of what we call X in our adder. This is what we call Y in our adder. This is K0, the input of the carry. This is K3, or the most significant bit is the carry out. And this is the actual sum or the output of the adder. Okay, so we will go ahead and just use constants for many of these items. So when you use constants, it is under wiring, and you just pick out the constant component. And by default, it has a value of 1, which you can change. So I'm going to change this one to a 0. So we can change the hexadecimal representation from 1 to 0. And then we can have another actual value of 1 to connect to Y. So we have a constant again. This time it's 1, but we want to increase the data bit to 8 because a register or an adder by default is 8-bit wide. So we have to increase the width to 8. And then the value that you want to specify is 0x01 because it's an 8-bit number. So we connect it here. So now we are specifying, we are adding 1 to whatever this input is experiencing. So the way we connect this is the output of the adder goes to the input of the register. And then the output of the register goes to the input of the adder. So we have a loop right here. A loop, so to speak. Okay, it's not really exactly a loop. Okay. All right. So right at this moment, you might expect the circuit to go crazy because the output of the adder is going into the input of the register, and then the output of the register goes back to the adder. So it should be doing something right now, but it's not doing a single thing. Why is it not doing a single thing?
No ticking.
Because there's no ticking. Clock is not ticking, and it's not even enabled. Okay, so this is a edge sensitive type of clock, but it is also triggered, which means en itself has to be a 1. So we're going to take another constant. Okay, in the other class I did not do it this way, so the other class did not need this extra constant, but that's okay. So we attach this extra constant to enable. Okay, but it's still not ticking because the clock line is not having any edges. It's not being ticked. We also want to make sure that we are not resetting this, so it is a good idea, even though it's not 100% necessary, but it's a good idea to connect a 0 to the reset pin. This reset pin is not active low, it is active high. So by connecting a constant of 0 to the reset pin, we're basically saying do not reset this register. Okay, we are basically just saying leave it alone, do not reset it. So what is left now is just the clock signal. So the clock signal is not going to connect to a pin. I'm going to choose something that is a little bit different this time. I'm going to connect it to a clock. So a clock looks just like a pin, except the notation is different. There's a little square wave in the inside, and you can click it just like a regular pin, a regular input pin. So let's see what happens when we click it. Whenever you click it, it changes the state. So right now the clock is low. If I click it, it becomes high, and if I click it again, it becomes low again, and so on. Okay? But before we click it, I want to know exactly what is going to happen when I click it at this point. What do you think is going to happen visually? What do you think you can see? The register value would change, right? It would change from 0, 0 to 0, 1, okay? So how do we know that it is about to change to 1? You can always click on the wire to find out what the value is. So when I click on this wire, which is coming out of the adder, it is saying, oh, it's a 1 already. Well, it's not surprising because the output of the register is the value that you can see in the register, which is 0. So if we're adding 0 to 1, the output of the adder has to be a 1. Is that okay? But that 1 is not getting stored because the register needs a rising edge on the clock pin in order to define the moment that it's going to update. Okay? So when I click this clock pin, then it will update. So observe the value of the register. Now it updates to a 1. Okay? And the falling edge doesn't do a single thing, and then the next rising edge will make it a 2, and so on. So do we have any questions about this really simple circuit called a counter? Okay, no questions about a counter? Okay. So what if you want to do this really quickly? You can try to click as fast as you can, and even with a gaming mouse, you can only click so fast. So what you do is you cheat. You go to the simulate window, and then you check the click frequency first. Okay. So the click frequency is basically auto clicking. Okay. At what frequency are we going to auto click? So at this point, the default is 512, which is rather fast. Okay. So if you want to visualize and actually see something happening, I would suggest something along like 8/4 or something like that. Okay. And then you go back to simulate and you enable ticks. And now the clock line is ticking all by itself, and you can see how the value of the register is changing. So do we have any questions about this operation? So a counter is possible only because we have clocked or edge sensitive circuitry. Because without that, we have no way to control the looping thing, okay? Because the output of the register, the output of the adder will try to update this guy, and the output of this guy will try to update the input. So there's no way to define the behavior. But in this case, we can define the behavior because of the clock circuit. Is that okay? All right. So the next question, which is not entirely related to this class, is what do you use a counter for? I mean, this is a very, very simple counter, but what do you use it for inside a processor or in a computer?
You could use it to like do things that happen on a recurrent basis, like every 90 ticks do this.
And what do you think your operating system is doing that is time-based, that requires timing?
Stuff with hard drives.
Okay, that's one.
Stuff doesn't explode out now.
What about multitasking, multi-threading, and all that stuff? Why do you think that has something to do with timing?
Gotta share time. Gotta share time.
They share the same processors, right? The same cores. Okay, you guys have multi-core processors, but it's still the same set of processors. So before we had multitasking operating systems, we had single-threaded, operating systems, DOS. Okay, so back in the DOS days, if you run one application, it takes up all the resources. Okay, until that application voluntarily gives up control and go like, okay, I'm gonna give the next application some time to execute. Okay, in other words, multi-threading or multi-processing relies on cooperation. What if something like a DOS prompt decides, I'm just gonna hog all the time to check whether someone is typing something on the keyboard. I'm not sharing. What do you think is gonna happen? It locks up everything. Okay, so would you like that? In your operating system where one single task is locking up everything else because it's not giving up control. That would not be a very good thing to do, would it? So what do you think the operating system is going to do when you have multiple processes? They all want to hog processor resources. They all have a lot of computation to do. What do you think the operating system or the kernel, which is the innermost part of an operating system, going to do? It will try to be fair, right? It will try to be fair, go like, okay, process one, I'll give you up to 15 milliseconds to do what you need to do. 50 milliseconds is up, and you're not ready to give up control. And the operating system will go forcibly remove control from you and say, okay, I'm going to give the processor to the next process, and you have another 15 milliseconds to do whatever you need to do. So that is one of the most basic feature of an operating system or kernel that relies on the timer. So something as simple as this, forms the most basic mechanism of a processor that provides the ability to do multi-threading in a fair way. When you guys move on to a 4-year university and take the operating system class over there, they will talk about these concepts. Okay, they will talk about the round-robin method of dividing the processor resources and give everybody a little bit of a share. So those are kind of more advanced concepts, but I'm giving you a little bit of a connection to those future topics that you will probably encounter. All right, so this is rather interesting. And the next thing we're going to do, okay, let me stop the simulation here because I don't need that anymore. Or just stop the ticks so that the circuit doesn't do a single thing anymore. So the next thing we will do, okay, we'll add a new circuit here, is to look into how memory works. Okay, and we'll start with a ROM. Okay, so we'll say ROM example, and then we'll go ahead and pull a ROM component out of the memory devices. So here's memory, and we look up ROM, and here's ROM. There we go. So you can see a ROM has 3 ports. There's one port labeled A, there's one port labeled D, and there's one port labeled cell or select. Okay. And because we already know how to look up the documentation in the browser, we'll just go back to the browser and find out exactly how does a ROM operate. So okay, 1, 2, many levels. We go to memory, or you can just Control F and look for ROM faster. There we go. So when you look at the ROM documentation, it would explain that A stands for address, D stands for data, and then cell SEL stands for select. Okay. So normally, okay, so let's explain your cell first, right? SEL. If cell SEL is a 0, the ROM is not doing a single thing. It's not driving the D port, it's not paying attention to the A port, it is just idling. Is that okay? Do you guys understand what I said when I said, you know, is the D port is not driving? Do you know what I mean by that? Okay. Yep.
Do you mean like the enable pin we had on like other memory where it just doesn't do anything if it's not enabled?
It's not exactly like that. The enable pin in a D flip-flop is enabling the update of the D flip-flop. This enable or this select is not quote unquote enabling, it is actually telling the device to specify content on the D port. Okay? So driving means, okay, so let me explain. I'm just trying to we don't have anything that can be that has the option of driving versus not driving. So I'll explain that later. Okay, so because you know, the only way to explain that clearly is when we have two ROM and we want both to drive the bus at the same time, then we have a problem. Okay, so I'll explain that later. So for the time being, you just have to kind of remember, you know, when I say driving the output, means we are specifying a value at the output. Okay, we are actually exerting, okay, we are putting effort into changing the zeros and ones and the voltage of the output, as opposed to not touching it at all. Okay? So A is an input port. It is an input pin. It allows somebody else, another component, to specify which location do we want to pay attention to. Okay? Cell is basically saying whether this entire chip should be paying attention or not, doing anything at all. And then D is for specifying the content of the addressed location. So the other way to look at a ROM, okay, which I think is beneficial, is to right-click on it, and then you can look at edit contents. So in this case, because we have a ROM module that has 8 bits for the address bit, it has exactly 2 to the power of 8, which is 256 locations. The location, each location is 8-bit wide because it is controlled by the width of the data bit. So let me say that one more time, okay? This is not a very good one. Let me change these, so that it's much more obvious of what I'm talking about. So let me change the number of address bits to 3, and we'll change the data bit width to 5, okay? So now it becomes a little bit more obvious. So when I right-click on it and go to edit content, it only has 8 locations this time. Why do you think it has 8 locations? It has to do with the width of the address. Why do you think it has 8 bits? 8 locations.
So it's 3 bits wide.
Because it's 3-bit wide, exactly. So when the address is 3-bit wide, it means the address can specify 000, 001, 010, 011, 100, 101, 110, and 111. Altogether, there are 8 possible addresses that you can specify when you have 3 bits. Is that making any sense? Okay? So now you can kind of imagine that you have this notebook here that has exactly 8 pages. And the pages are numbered in binary. Is that okay? But the content of a page has nothing to do with the number of bits that you use to specify the page number. Okay? The how big each page is or how much data you can store in each page has to do with data bit width. So in this case, I'm specifying 5 bits. So that means each memory location in this ROM can store exactly 5 bits. Now it is still using 2 hexadecimal digits because 5 bits requires 2 hexadecimal digits when you can only have hexadecimal digits. Is that okay? So I'm going to start to specify some random content here. Okay. So 1, 2 is 1. You cannot have 2 something, by the way. Okay, the most significant digit of the 2 digits here can only be either a 0 or 1. Because 1 hexadecimal digit takes care of 4 bits, right? So that means the least significant the least significant hexadecimal digit is accounted for 4 out of the 5 bits already. the most significant hexadecimal digit is only going to specify the leftover bit as its own least significant digit. So that's why we can only specify 1 or 0 for the most significant hexadecimal digit. Okay, so this one I can specify 0, 02, 0F, 1D. See, if I type 2, it's okay because it's 02, but the moment I type 5, it doesn't like it. The 2 goes away. Okay, so and then this one can be 10. This one can be 0E, and I'll make this one 07. Okay, there we go. So I have just randomly put some content into the ROM, but later on I can retrieve these content. Okay. When you have these content in the ROM and you think, oh, this is kind of important, I want to save it, you can click on the Save button, which will allow you to export the content of ROM into a file so that later on you can load it back into the ROM. So this is a really useful feature because it allows you to specify the content of ROM from a file, which is basically just a text file. Okay, so we're done with specifying the content, and you can see that they are also reflected here. So the next thing we want to do is to let me just duplicate this. Okay, so now we have 2 of the same thing. They have the same content. With the second one, I'm going to change the content a little bit so that they are not exactly the same. That's a different. It's a different window because I think with the first one, I changed the address bit width after I started the editor, so it didn't change its appearance, but this one is starting with a different one. So I changed this to 0F, 13, 07, 12, 15, 0D, 02, and 11. Okay. I just wanted to make sure that they're different, that's all. Okay. All right, so now what we want to do is we want to be able to specify, I want to make it work, okay? I want to say, okay, the first ROM, I want to look at location 2, tell me what it is, okay? So the first thing you need to do is to do the select here, and I'm going to use an input pin for the select because this makes it easier for me to change and go like, okay, let's select now, let's not select now. And I'm going to have a different select pin for the second one, so this way I can demonstrate what it means when you have 2 ROM trying to drive the same wire at the same time, okay? And then the address is another input pin, okay? So we can make this a 3-bit input pin because it has to match the width of the address bus. So this is going to be a 3-pin thing, and I just need to duplicate this to another 3-bit thing for this guy. So now I can address each one individually. This gives me enough control to demonstrate how to specify how to specify what location to look at in the ROM. The first thing we want to click is data. If I click it here, okay, it doesn't specify anything. Let me hook up a wire first because that may make it more obvious. So I'm going to hook up a wire first and poke it. And it says question marks, XXXX. What do you think that means? There's no content of that wire. Nobody is specifying what content should be on that wire. That's because the data port is not driving. This chip is not driving the data port at all at this point. Okay? So the next thing we want to do is to change the select pin from a 0 to a 1. And right at that moment, okay, right at that moment, the chip starts to pay attention to the address bus or the address pin. And since the address pin had a default value of 000, it is now saying, oh, you want to look at location 000. It has a value of 12 in hexadecimal. But that content is also being driven, the ROM chip is using that content to drive the data port. So when you click on the data port at this point, it's going to reflect that. Because if we have a 1, 2, this is 1, this is 2. Is that okay? Because 1, 2 is in hexadecimal. 2 in hexadecimal is 0010, and 1 is obviously just 1. Is that okay? What about that -14 thing? Imagine you have your number circle for 5-bit numbers. That's what -14 looks like as a signed value when you're using 5 bits to represent it. Is that okay? Are we okay? You guys you don't seem to be convinced. Okay. So how do we make sure that 10010 in fact is you cannot see the 4. That's why you're not convinced. Okay, let me. There's a button here to. There we go. Auto. There you go. Now you're more convinced. Now you're not convinced because when you look at 10010, you go like, okay, this is a 2, this is a 16. 16 plus 2 is not 14. So how come this is -14? Remember 2's complement? Okay? 2's complement is doing the same job as arithmetic negation, right? So if 10010 is really representing the value of -14, if I take 2's complement of the same bit pattern, I should get back to the binary representation of 14 itself. Is that making any sense? Yes. Tell me yes. Just say yes. Okay. Okay, so what is 2's complement? It's 1's complement plus 1, right? We can do this mentally. We don't need a piece of paper. Because you're just flipping the 1's to 0's, right? So it becomes 0, 1, 1, 0, 1. Okay? And then you add 1 to it. So it becomes 0, 1, 1, 0, 1 plus 1, which becomes 1, 1, 1, 0. Right? So 1, 1, 1, 0 in binary is what? It is 2 plus 4 plus 8. That turns out to be 14. So it checks out. Okay? So every time you see something that you are not really sure, you should question it. Okay? And find out what is it? Why does it display this value? Is it correct? Is that okay? Okay. So we're going to do the same thing with this one now. Okay, so we will go ahead and let's specify another location. This is 12. We'll specify something that looks like it but not exactly, which is this one here. Which location are we looking at?
7.
This is location 7. No, not 7. Location 6. Because this is location 4, this is 5, and this is 6. Location 6. So how do we specify location 6? With the address pins. 110. Very good. Okay, so 110, and then we have to select the component because otherwise it's not paying attention at all and not driving the output. Okay. And then we click on we draw a wire first, and then we click on the wire, and we should see 02 as the value on that pin. So we click it. Okay, sure enough, no big deal. So now what we'll do is we'll connect these 2 wires, and then we'll say, what is going to happen when we connect these 2 wires? What do you think?
They're both output pins, right?
Okay, think of it like this. Okay, think of a board. Okay, so think of a board like this, and there's one ROM chip on each side of the board. Okay, and for each bit, it's kind of like a peg that is accessible from both sides. Okay, so if you want it to represent a 1, you push it up. If you want it to represent a 0, you push it down. Okay, but it's the same peg, basically going through the board, and then each ROM controls one side of the board. Is that okay? So for bit 0, we don't have a problem. Let me click on those pins again. So for bit 0, we don't have a problem, do we? Because, okay, we need a poking tool. So bit 0 is not a problem because bit 0 is a 0. So both ROM chips will try to push it down, right? And it's not a problem because you push it down, I push it down, and it's down. Okay, not a problem. Bit 1 is not a problem either because it's a 1 for both in both cases. So we don't have a problem until the most significant bit. For the most significant bit, the top ROM chip wants to push it up because it's a 1. But the bottom ROM chip wants to push it down because it is a 0. But it's the same peg. So what do you think is going to happen? Hmm? It doesn't freeze. It's actually the opposite of freeze. What is the opposite of freezing? Melting. Okay, so, but in a physical sense, what is happening with the most significant bit is one side, the top chip, is trying to push that peg up. Okay, but on the other side of this board, the other ROM chip is trying to push it down. So now it becomes a competition, right? It becomes, it's just testing who is stronger. Who's doing all the work? What do you think is behind the scene, actually changing the voltages and switching and doing all sort of things? You have to go all the way back to the first week in this class. Transistors, very good. Okay, so what type of transistor connects to the higher, the top rail, the voltage that is positive? The P transistors. And what transistors connect to the lower portion? The N transistors, exactly. So the tug of war is really between the P transistors versus the N transistors. Now this is not a device physics class, and I have no idea about the device physics. But I'm told that N transistors are always more efficient. In other words, the N transistors usually win. So in this scenario, if these two wires are actually connected, this guy is going to win. Because the strength to pull a line low is usually higher than the strength of pushing it up. Okay? But what we do end up with is a crowbar. Okay? A crowbar means the top rail. Okay? So you imagine the top rail and the bottom rail, they are now connected through transistors. So what happens when you, okay, don't do this at all. Okay? I'm just hypothetically asking you what's going to happen. Okay? What happens when I have a wire, like a small thin copper wire, and with insulated gloves, okay, I put those into the electrical outlet. What do you think is going to happen? Depending on the thickness of the wire, your circuit breaker may trip, right? But if the wire is thin enough, what do you think is going to happen? It's going to glow, it's going to get very hot, and it's going to melt, and in a certain section of the wire is going to disappear. Like literally disappear. Because it becomes copper oxide, and then which is powdery, and then it just kind of drops, and you don't see the copper metal anymore. Okay? And that's going to be what happening to your transistors too. So that silicon, is going to melt. It's going to vaporize. Okay? So I was incorrect. It's not melting. It's vaporized. And when I say vaporized, what is the result? What is the state of the material when something is vaporized? Turns into gas, right? How much volume do you think you have inside the package of a chip to contain gas that is hot? Not a whole lot, right? So what's going to happen? It's going to explode. You guys are looking at me and go like, nah, that cannot be the case. So I'm ready for that moment. So we'll go to YouTube, where you find the most trusted news. So between Saturday Night Live and YouTube, that's how I got all my news. Good summary. Give me the most important points. Watch Saturday Night Live. Okay, so we want to look at Amd Processor Explode. There we go. This is the one. And we're going to magnify this. So somebody was running a benchmark program to maximize the processing of the processor to make it as hot as possible. And it is still attached to a heatsink right now. So we are showing the clock speed and temperature, current temperature and stuff like that. And then the person is gonna just remove the heatsink. Yeah, I'm starting to get a little motion sickness. And poof. Okay, so if this is in slow motion, you can see how it exploded. And most people stop right here and go like, oh, okay, so it exploded up, right? You know, everything just vaporized up, and that's the end of that chip. That was not what happened. So what you need to do is to keep watching. And now they're taking the camera over the desk, and they punched a hole through the particle wood. Yep, that's what happened. That's where the gases are going. Okay. In other words, this person just turned an AMD processor into what we call a shape charge. So I was incorrect when I say melt. Okay, when I said melt, I was incorrect. It was actually vaporized, and that's what's happened. You know, well, this is not happening because of a what we call bus fight situation, which is what I'm trying to describe in the notes. But when you have sufficient bus fight, or when you have components on the circuit trying to fight, to change the state of a particular line, that can happen. Okay. So in Logisim, what do you think is going to happen? Logisim is not going to vaporize. It's not going to vaporize your computer, right? We certainly hope not. So we'll see what happens. Ding! The line turns red. Okay, when the line turns red, you need to click it to find out what is wrong with it. Okay, so we're going to check it out and find out what's wrong with it. And you can see that it reports an error because there's no way to interpret these bit patterns anymore because one is quote unquote erroneous. The 0010 is fine, that's not a problem because both ROM chips are trying to push and pull in the same direction, so they're fine. But the most significant bit where the top ROM wants to push it up and the bottom ROM wants to push it down, now we have what we call a bus fight. No, I'm not kidding, this really is called a bus fight, okay? So now we have a bus fight, and Logisim just says, I cannot determine the state of that particular wire because one wants to push it up, one wants to push it down. I have no idea what to do with it. Is that okay? So all of this is set up to explain, earlier when I said, this component is driving the output versus not driving the output. So what we want to do, what I want to do now is to click on the select of one of these two ROM chips. Let's say the bottom one, okay? If I click this one and deselect the bottom ROM chip, the bus fight goes away because now the bottom one is not driving the bus anymore. In other words, in the analogy of a board with all the pegs, the bottom ROM is now not touching the pegs at all. It's like, oh, okay, I'm not touching it. So whoever else is trying to push the pegs up and down, they can do whatever they want. I'm not touching the board at all. I'm not touching any one of the pegs. Is that okay? So is that helping to explain what I mean by driving the output? So when you're driving the output, your hands are on the pegs and you're trying to change it one way or another. When you are not driving the output, your hands are off. You're not touching it at all. Is that okay? Yep.
How do we know that the D is taking input from the wire and trying to...
Data is the output. So D is the output. If I enable this one, then they both try to drive the output, but they are trying to drive in different directions on the same bit.
I'm saying, how does the ROM know what the wire has?
Which wire?
Because isn't D an output?
Yes, but it's an output for both.
So why would A know about what the other bus is doing?
They don't.
So then why are they fighting?
Because 1D is trying to specify, this one is trying to specify 10010. This one is trying to specify 00010.
That one doesn't know.
But they're connected to the same wire, same physical wire.
Okay, I'm just wondering how they would work, I guess.
It doesn't work, that's why it's red.
Well, no, I mean how the ROMs work, how they operate.
Okay, okay. So the way the ROM works is once it is selected, it looks at the input, and then the input is going to select which location becomes the output. It's array indexing basically. If you look at the ROM chip as an array, this is what you put inside the square bracket in C, and this is the value of the result of indexing.
So why is that affected by what the other one's outputting?
Because they're connected to the same wire. The wire can only have one single voltage. Okay? Because the wire is a conductor, it can only have one single voltage. But when one side wants it to be a high voltage, the other side wants it to be a low voltage, now you have a problem because which voltage should it be? Is that making any sense? Okay.
So if one puts out a 1 and the other one wants it to be a 0, then what can it do about that?
What I said earlier, vaporize. I'm not kidding, because when you push a lot of current through a very small semiconductor device, it will get hot enough to vaporize itself. We are talking about a very small amount of current here. We're talking about at the most maybe 10 milliamps, which to most of us is like, well, 10 milliamps, it doesn't do a single thing, right? But you have to remember, we're pushing 10 milliamps through a 14 nanometer transistor, which is tiny, okay? So it's gonna blow it up. One of these, a few transistors is gonna blow up because of this, because of this configuration. Is that okay? How many of you are taking electronic classes over at ET? Okay. If you okay, this is positive voltage, and typically you have a load, okay, and then you have an N transistor, and then you have ground, and this is the gate to control whether you want to turn on or turn off the load. Okay, so the load in this case usually is something that is not inductive, so you don't want to do a motor thing, but it can be a light bulb, it can be a LED, depending on how much current your transistor can handle. Okay. So now the question is, what do you think is going to happen when somebody says, I'm just going to eliminate the load and just stick a copper wire between the terminals of the load? What do you think is going to happen? You turn on the N transistor, right? And what's going to happen? This is a positive voltage, right? This is a negative voltage or 0. So now you have a large amount of current going this way. Now, the transistor, even though ideally speaking it has no resistance, but in reality it does have resistance. So it has a little bit of resistance over here. When you have resistance and you have current, what do you get? A voltage drop, right? So the voltage drop is I times R, and then you times I one more time for the power. So you have I squared R, which specifies the power that is dissipated by the transistor as heat. That is why it's going to explode, because it just cannot handle that much heat. So the material inside the transistor, the silicon, and whatnot, is going to vaporize, and then if it gets hot enough, the whole thing would rupture and actually quote unquote explode. But that is the same kind of scenario as what we are talking about here, because what we are looking at is what is equivalent to having an N transistor, this guy, and another one is having a P transistor up here. So P transistor in our case looks like this with a bubble. So There's a resistance here too, so whichever one has a larger R is gonna blow up first. Because they have the same I, right? Because this is a single wire, so whoever has a larger R has more resistance, is gonna have to dissipate the more heat, and it's gonna die first. And save the other one. Is that okay? Okay, all right. So what are we going to use ROM chips for? Oh, by the way, what is ROM? How come it's called ROM? Read-only memory. Yep, exactly. It wasn't invented by Romulans. In case you were wondering, no. So it's read-only memory, which means you can only read from it. I mean, there's no way you can actually overwrite the content of ROM. It doesn't give you the pins to do it, right? So physically, in the real world, how do we get content onto ROMs?
It's already coded.
Hmm?
It's already pre-coded.
It's pre-coded. Okay, so it depends on the ROM technology. This part is not going to be in any one of the tests, but it's kind of cool to go through all of these things. So when we talk about ROM, there are different types of ROMs. In the really, really good old days, we have what we call Otp Rom. OTP stands for one-time program or one-time programmable. So it's factory programmed, and once it's programmed, you cannot change the content at all. Okay. And then we have Eeprom or Prom, P-R-O-M, which is P-R-O-M. There we go. So Prom stands for programmable read-only memory, which is kind of weird because if it's read-only, why can we program it? So it turns out that sometimes people make mistakes in their firmware. So occasionally you might want to get some blank ROM so they can reprogram those and then ship it to your customers. Okay, so that's Prom, and these are one-time reprogrammable. Okay, so they come to you blank. You use a special device, you put a chip onto the special device, you specify the content, you hit a button, and you can program it once. Once it is programmed, it physically removes certain fuses on the chip. So once you program it, you cannot deprogram it anymore. Okay? So when we say Prom, they are one-time programmable. Okay. So then we go to Eeprom, Eeprom. The E stands for erasable, which adds to confusion, right? So now it's erasable, programmable, read-only memory. So now the question is, if it is erasable and reprogrammable, how do we do it? It's using an optical window. Okay, you guys may not have seen it because you guys are way too young, but if you ask your uncle or your older relative, they might show you a Eeprom. It is a chip that has an optical window. Usually it's circular, but occasionally it can also be rectangular, but it's transparent. Okay, so the way it works is if you want to erase the program on the ROM, you expose it to UV, ultraviolet light. And yes, sunlight works too, but it takes a long time if you expose it to sunlight. Okay, if you put it into a chamber where a UV fluorescent light is only about this far away, it takes about 15 minutes to erase the content. Then you can reprogram again. So that's why it's called EEPROM, because it's UV erasable but electrically programmable read-only memory. Is that okay? Okay, but that's not the end of the story. Then later on we have EEPROM, double Eeprom. The first E stands for electrical. Electrically erasable, programmable, read-only memory. Which basically means you do not need that UV light anymore. So you can electrically expose your ROM to a different voltage, and the higher voltage, or whatever voltage you specify, can electrically erase the original program, which allows you to reprogram it again. But this also takes another device. You have to remove the ROM chip, put it onto another device, reprogram it, and then put it back into your socket. Do you have to do that when you update your apps on your phone? No. Why do you think you don't have to do that? because we have progressed from EEPROM to flash memory. So flash memory is also a form of read-only memory, except we don't call it ROM, but it is really read-only memory for the most part. It is only programmable through a special sequence, but it does not need a special voltage. So that's why they're really handy on devices, because now you can receive an update through your network, and you can now, without removing any component from your board, from your actual circuit board, you can now reprogram the content. And from flash memory, we lead to SSD or solid state drive, which is basically flash memory arranged in a certain way. But it's not just flash memory. What do you think is the biggest problem with SSDs?
It's a little slower speed.
It's not slow, it's really fast.
They wear out faster.
They wear out. Okay, I like that. Why do you think they would wear out? There's no mechanical components, right? It's not like a hard drive where you have a spindle that's rotating at 10,000 RPM. I mean, you can kind of imagine the kind of mechanical wear you have to deal with when something is spinning at 10,000 revolutions per minute. So solid state drives do not have any mechanical components, so how come it's wearing out?
They have a set amount of reads.
Write cycles. Okay, they're write cycle limited. When I was still in the industry, they were rated at about 100,000 write cycles. Is it still about the same, or have they changed?
I think I saw 1 million.
1 million? Okay.
I might be wrong.
But we have to remember, new operating systems and new processors are also faster, so it doesn't take as much time to hit the 1 million write cycles. So they will, basically, wear out eventually. Okay, but that's at the chip level. Okay, at the chip level, they do wear out. Now, when you look at certain file systems like FAT, file allocation table, they like to overwrite the same sector over and over and over and over again. So if you don't manage which sector you use, then SSDs will burn out in no time when you use file allocation table file systems. Okay? So how come, it's not doing that?
It's separating it out like you do on a farm. You use this for a while, you use that for a while, you
Yep,
use this for a while.
exactly. Your SSD drive is actually a computer itself. It has a processor, it has its own program to manage how to do the rotation, and they call it load balancing. Okay, they monitor how many times this particular sector has been overwritten, and it monitors overall, which sector has been overwritten how many times, and then it would go like, oh, this particular sector here has not been overwritten enough, where the other ones have been overwritten a lot. So it would do the load balancing, which basically means what you know as sector 0 physically on the chip can move from one chip to another chip to another chip to another chip. It's doing the load balancing for you. Your SSD drive itself is a computer. It is programmed to do load balancing. So it's just kind of interesting how all of these things evolved over time. In how many decades? I would say from about the 60s to the 70s. So I would say time-wise, we are talking about 1960s here, and we are talking about 2010s over here. So we are talking about a time span of only about 50 years, which is not a whole lot of time. You open the hood of a car from the 60s. You open up the hood of a car from this year, assuming they're both gasoline engine. The change is there, okay, but not the same degree. Your new car is not millions of times faster than the other one. Let me put it that way.
It just has more electronics. It still runs the same though, unless it's an electric.
The control system has come a long way. From carburetors and mechanical ways of regulating gas, air, gas. How do you call it? Mixture, huh? Fuel. Yeah, fuel, air, fuel mixture. Yeah. So now it's all electronically managed timing, when the spark plug goes off, that's also electronically managed. But when you look at the basic design, the cylinder, the combustion, the valves and stuff like that, that really hasn't changed all that much. Okay, it's kind of still the same basic force cycle. But when you look at this kind of technology, it's completely different. Cool. All right. So do we have any questions about this particular picture? No questions? Okay. Now, in an actual computer, the output of ROM chips are actually connected, just like this. So what do you think is happening to prevent cases like this? Not heat sink. This is not a desirable condition at all. You want to completely avoid it.
They'll just use the same clock and only have it set to pick one at a time.
You only want one chip to be selected at any particular time. That's how you manage it. Yep. Yep. Question?
So if it's off, then whatever's coming out of the bottom one can't go into the top one?
It never goes into the top one. It really is just fighting on the outside. Okay, remember the board example? So in this case, the top ROM chip is no longer touching the pegs on the board. So when you're not touching the pegs, you can still observe if you want to, except that this chip is not observing. But it's not touching it, which means the position of the peg is now up to the other chip to specify. If I turn off both chips, okay, this is a good question. If this is a real circuit, if I have this configuration and both chips are not touching the pegs, what's going to happen? The pins or the wires are now said to be floating. So a floating wire is basically just a wire, just like, if you just kind of imagine that I'm holding a wire on the insulator, so I'm not even touching the actual conductor part, so I'm just holding a wire like this. That is a floating wire, okay? But what do you think is that wire experiencing?
Induction.
Induction, very good. So induction has to do with magnetism, okay? A changing magnetic field would induce your current. So that wire at this point is actually not nothing, okay? There's always some kind of electrical potential on it, on the two ends, except it is induced by the external magnetic fields. Yep?
Do they try to actually, isolate it from the rest of the circuit so that it doesn't get inductance? If there's some sort of non-conducting material to prevent that?
You cannot stop inductance because as long as you have a conductor that has a certain length, you can always induce something. So it's usually okay, to have it floating as long as nobody's paying attention. In other words, if no one is reading the state of this wire, it's okay to have it floating. It's not a big deal. Okay. The only time you don't want something to be floating, or this can cause problem, is when you have a EMP device going off, because then the wire will pick up a large current will be induced, or high voltage will be induced, and then it will just zap the components connected to that floating wire.
That's what I was wondering, if there was a lead lining around it or something.
No. Typically, we usually, inside any electronics, at any particular time, some of those wires will not be driven by any components, and it'll be left floating. So it's okay, unless you have a electromagnetic pulse nearby, then the wire will pick up the pulse and fry the components next to it. Or in some cases, if you have a headphone, like a wired headphone, it will actually pick up electromagnetic inductance. So that's why, sometimes, when you're listening to music and you're close to something that emits a changing magnetic wave flux, it will start to pick up things.
That's great.
Yep. There was a hand back there a little bit earlier. No, you're good? Okay. All right, so today we talked about ROM chips. Over the weekend, I want you guys to read ahead of me, and I already talked about what I want you guys to read about. So you want to go to the plexers and read about multiplexer, the demultiplexer and the decoder. They are all related, okay? And for those of you who have a problem with, these terms, like multiplexers, demultiplexers, and these things in the context of an electrical circuit, go watch Thomas the Train. No, I'm not kidding. Go watch, Thomas the Train and observe, how Sir Topham Hatt, programmed the tracks. Okay, who's going to go where? Percy, you're going to go to that station, and Thomas, you're going to go to that station. How does Sir Topham Hatt make that happen? Okay, multiplexers. Okay, so now you have a kind of physical view of what a multiplexer is.